So here we have a challenge problem. This is extra credit, and we are asked to find an expression for the distance d up the incline that the object is going to end up. And we are asked to maximize d for a given theta, and then figure out what that d is going to be. That this answer d is going to be in terms of all of these variables. It's not going. We're still not getting like an actual number yet, since we can't know our initial velocity. So find an expression for distance d up the incline. Well, we know we have a point d. Wait, what are the x and y coordinates of that point? Well, we have x, which is, well, it's d times cosine phi, and y is d sine phi. This just comes from this triangle here. D is the hypotenuse, and phi is that angle. So here we have an expression for the final position. And of course, we are assuming the origin to be where the object starts. Now, how do we figure out the distance d? Well, we can write two position equations and see that, well, position of x is the initial x times time. There's no acceleration, there's no initial position, so this is all we have for our initial equation for position. Now v initial x, well, how do we write that in terms of vi and theta? Well, we know it's vi times cosine of theta, and that's multiplied by t. And this just gives us our x component in terms of vi and theta. And this is the equation for x. Moving on to y, we find it to be, well, we have a viy times time plus 1/2 at, and a is going to be negative 9.8, and then t squared. And we can go ahead and do the same thing we did with x. We can convert our initial y into vi, and this time it's going to be sine of theta times time minus 4.9 t squared. We're just simplifying that negative 9.8 over 2. And here we have another equation for our y distance. So now that we have the position equations for the x and y axes, well, we can sort of relate this y final position with our point we had up here, right? Our x is d cosine phi, and that's equal to now this vi of cosine theta times time. And we can do the same thing for y. Let's just scroll down a little bit here. Or we can say d of sine theta, sine phi, my bad, equals di sine theta time minus 4.9 t squared. And so we have these two equations. Now, what we're going to want to do is solve for t, right? We have all these unknown variables, and when you look back, it says your expression should be in terms of only these four variables. And we notice that, well, it wants g is one thing. So we kind of know we made a mistake there by changing that negative 4.9. Because maybe you have a different force of gravity, maybe you're on the moon or something like that. So you have g over 2 minus g over 2. We're just going to leave it as g instead of 9.8. We don't have a time here. This is a big thing. We don't have time. We want to get rid of that. So we have to sort of find time. We can get a t equals, right? T equals, we're going to divide both sides by v initial cosine theta. So it's d cosine phi over v initial cosine theta. And we can take that expression for time, plug it into this other equation. So we have d sine phi equals the initial sine theta. And now we're going to plug in this expression for time of d cosine phi over v initial cosine theta. We have to do that one more time for this t squared. whoops, it's going to be a phi. Very important not to mix up any angles. So we have an expression. All we have to do now is get d by itself. And this is a little bit tricky. It's not too bad, but there are so many terms that you have to be really careful. You don't lose any. So, so we're going to try and do some algebra to get a sort of d equals. Just try and find what d is. So the first thing we see we can do is distribute that squared. And we're also just going to rewrite some of these fractions just so they're a little bit clearer what's going on. And so we can sort of combine them into one fraction. See that? Right, we're starting to see things like the initial canceling out. And other sort of interesting, helpful algebraic steps. Now each of these terms inside that squared are going to get squared, right? Gotta make sure each one of them is squared. Now we see we have a d in each term. We have the initial canceling out. And so we have sine b equals, well, this is just tangent. Sine over cosine is tangent. We have to make sure that the angles are the same. We can't combine a phi and a theta. The angles must match. This is multiplied by cosine phi. And then we have minus g d cosine b squared over 2 bi squared cosine theta squared. So now we see we only have one d, and we want to get that by itself. So we want to get just this sort of term on its own on one side of the equal sign. So we're going to move it over here, and then we're going to move that sign back to the other side. So what that's going to look like is that original term. We're not going to do any algebraic steps within each term. We're just sort of rearranging their order. So we've added this term to both sides, and then we have that tangent theta cosine phi, and we're subtracting sine phi from both sides. So the next algebraic step here is going to be to multiply both sides by the denominator. So we're going to have 2 vi squared cosine squared theta times tangent theta cosine phi minus sine phi. And so we can actually make one step, which is very tricky to see coming. What we're going to do is just take one of those cosine thetas and multiply it into that expression. The reason why is, well, we're going to have cosine theta, and we're going to have sine theta over cosine theta, and we're just breaking that tangent apart. We have cosine phi minus sine phi. So we've broken that tangent apart. Now we can see those two cosines are actually going to cancel out. GB cosine squared of phi. All right, just writing this whole expression out a large number of times can be tricky to not make a mistake. But we see we have sine theta. We made a mistake up here. We forgot there's a cosine theta tacked on there. Sine theta cosine phi minus sine phi cosine theta. Why did we do that? Why did we just take one of those cosines and multiply it in? Well, it's because this right here is actually a trig identity, where we have sine of an angle theta times cosine of a different angle phi minus sine of phi cosine theta. You can see the angles are swapping and there's a subtraction sign. And we can know that this is equal to sine of theta minus phi. And so this is a kind of tricky identity because we don't really see it a lot. But if you know that that exists, it can make simplifying this much easier. You're going to get a nicer expression as your final answer. But I think if you keep everything just as in terms of these variables, and you get, as long as you get a d equals, even if you don't have this completely simplified, I think you will still net yourself some extra credit points. So we now can see we have GD cosine squared of phi equals 2vi squared cosine theta. Now we can apply this identity. We have sine theta minus phi. The last step is just going to be to divide everything by g times cosine theta, right? Because we want that d by itself. And that is the last thing over there, keeping it from being by itself. Oops, theta. Right, so this is tricky. This is pretty hard to do. There's a lot of algebra, there's tricky identities. And so that's why it's just an extra credit problem. But it's kind of interesting to see how we can do this. Now, part B, go all the way back up, says to figure out for what value of theta is d a maximum, and what is that maximum? Well, if you remember, how do we find the maximum of d? Whoops. Well, we have to take its derivative, right? Using the ideas from differential calculus, we know that when the derivative of a function is 0, it is at a maximum or a minimum. And so if we can derive this function with respect to theta, so we're doing d sub d with respect to theta, right? That's going to give us, when this is 0, it's going to tell us what our maximum d is. So I am not going to explain how to take this derivative because it is pretty complicated and not something that directly pertains to the physics of this class. I would recommend using a derivative calculator and just plugging this in and taking the output that it gives you, just so that way you can focus on the physics rather than the sort of derivative calc behind this. That would be a problem that is harder to solve than we would like. But we do find this result. Oh, whoops, this was supposed to be a phi. That is my bad. This is the derivative, right? When is that? We set this equal to 0, and we see we're just trying to get cosine of 2 theta minus phi to be equal to 0. Which is kind of weird, right? What this means is we want this function to be 0. So any of these terms in the numerator, 2 or the initial squared or cosine of that function, if any of those are 0, our function is 0. Our derivative is 0 at that point. And 2 can't be 0. The initial can't be 0. But our cosine 2 theta minus phi, that could be 0. And that could give us our maximum. So we want to set this to 0. So we know that cosine is 0 at pi over 2, 3 pi over 2, and so on. And we're just going to use the first solution. And so we know that inside 2 theta minus phi needs to be equal to pi over 2. And if it is, then this term is going to go to 0. And so now all we have to do is solve for a theta, right? Where theta equals pi over 2 plus phi divided by 2. And well, pi over 2 is 90 degrees. So why don't we just change it to degrees? It's a little bit easier to work with. So taking this expression, which of course we've changed just a little bit, we've got that division by 2. We plug that back into our original equation and sort of simplify a little bit. We know that plus phi over 2 minus phi is going to give us a negative phi over 2. And cosine 45 plus phi times sine of 45 minus phi can be simplified to 1 minus sine of phi. And that is another identity, which is a little bit tricky. And so this is sort of why this problem is extra credit not required is because of so much trig simplification that you have to do, right? You have to understand 45 plus phi, 45 minus phi over 2. Oops, this is phi over 2. Right? That this identity translates into 1 minus sine of phi, right? It's a little confusing. And personally, I wouldn't have known this. And so I would recommend just, if you're going to approach a problem like this, don't be afraid of turning it in an answer that's a little bit more complicated. If you can't get that simplification down, but as long as you can get an expression, you're still going to get that correct answer. You might lose some points on the problem just because, it's not fully simplified. But that can be, very tricky to get down. And we see that 2 actually cancels out with this identity. It looks like 2 cosine of a function, sine of a function, cancels out altogether into this 1 minus sine of phi. It's a little confusing. This is the final answer for part B. And it really relies on everything that you've done so far, which is a lot, being entirely correct. And so this is a very tricky problem.